So, welcome back to this second half of today's lecture. Now I want to discuss about the chain conditions. Namely, more precisely, if a module is Noetherian, is the S inverse of that module is also Noetherian, or if the module is Artinian, is the S inverse of that module is also Artinian, and things like this. So, before I start the study, I want to recall one definition which you might have heard in basically course like set theory or even the course like discrete mathematics and so on. It's very useful language. So, let me define. So, definition. An ordered set x less equal to. So, a set with an order means reflexive, transitive and antisymmetric relation. That together with a set is the pair is called an ordered set. Normally in many modern books it is called a partially ordered set, but as you have seen earlier also I am using only ordered set. So, if you have an ordered set, is called a lattice if for every pair x y in X, both supremum of the subset x less x y and infimum of x y exist. Exist in X, of course, in X. So, what is the supremum? Supremum is look at all upper bounds of this set x and y and take the least among them. Similarly, infimum is take all lower bounds of the set x and y and take the maximum of the lower bound. So, this is the minimum and this is the maximum. They should exist, then you call it a lattice. For example, so let us write down some examples. One, if x less equal to is totally ordered, that means any two elements are comparable, then it is a lattice. Or more concrete example, suppose you have a set y is any set and let us take a power set of y. This is the power set of y. That means set of all subsets of y with natural inclusion as an order. So, we are considering this ordered set Py and natural inclusion. This is a lattice. And what is the supremum? If I have two subsets A and B, if A and B are two subsets of y, that is there are two elements of the power set, then sup A comma B is A union B and inf A comma B is A intersection B. So, these are obviously the supremum and infimum in this power set. So, set theory basically we study this power set with this order. Alright, and one more example. If A is any ring, always commutative for us, then the set of ideals IA, this is the set of ideals in A, this is a lattice with respect to the inclusion, of course. So, that is, we are considering this IA inclusion. This is a lattice. So, I have to tell you what is supremum and infimum. So, supremum of two ideals A comma B, obviously it is A plus B, and infimum of A comma B is intersection. This is obvious. This is an upper bound for A and B, and it is the smallest upper bound. Similarly, this is, and we have been studying this lattice. Alright, one more example. Fourth, if V is an A module, then the submodules A submodules of V we have denoted by this S A of V with respect to the usual inclusion. This is also a lattice. And what are the supremum and infimum? Obviously, sup, if I have two submodules V prime and V double prime, that should be V prime plus V double prime, the smallest submodule of V which contain both. So, V prime and V double prime are submodules of V, A submodules. Then we know the sum is the smallest, so that means it is a supremum. Similarly, the infimum V prime V double prime is precisely the V prime intersection V double prime, and both are submodules. So these are the supremum and infimum in this set. So we have been studying, for each module we have been studying this lattice. Alright, now one more definition I will need it. So if I have two lattices, what is the homomorphism of ordered set? Homomorphism of ordered sets is precisely the map. So, f x less equal to, and I should actually write now there are two orders involved. So, this is suffix x, and y less equal to y. These are two ordered set, and a map between them is called a homomorphism of ordered sets if it should preserve, if x less equal to y, x less equal to x prime in x should imply f of x less equal to y f of x prime. If this, so that means it is should be increasing map, then it is called a homomorphism of ordered set. Similarly, we can talk about homomorphism of lattices. That means it should not be only ordered homomorphism of ordered set, but it should also respect the sup and inf. So similarly, one can define homomorphism of lattices, and what should be? So it should preserve order, it should preserve sup, and it should preserve inf. If so, I will write quickly sup of x comma x prime and sup of fx f x prime. So, f is this and inf of fx f prime. So, you make a definition. So, I will say make this more precise. I may not use it so often, but just because we defined a lattice. Okay, so what did we do in earlier lectures? Now let me put in this language. So we have, so let A be a ring S multiplicatively closed set and V be an A module. And remember, now I want to discuss if V is Noetherian or not. If V is Noetherian, then what happened to S inverse V, or if V is Artinian, what happens to S inverse of V, and so on. Or when it is a ring, what happened to the ring S inverse A, and so on. So then we have this S inverse A, S inverse V. These are all submodules of S inverse V module as S inverse A submodules of S inverse V. So note that here we have this iota map from the ring A to the ring S inverse A, and then for V also we have this map. This is iota V suffix S, this is iota AS. This is a ring homomorphism, and this made this S inverse V as a S inverse A module, so this makes sense. And then we have S of V, these are the submodules of V, and I want to define a map here. Alright, so let us recall a definition of Noetherian module. That means this ordered set here with respect to inclusion has maximal elements. If it has minimal elements, then we say it is Artinian. If it has maximal element, then we say it is Artinian. Alright, so we have a map here, namely if I have a module, if I have a submodule W of S inverse V, this is S inverse A module, S inverse A submodule. And how do you get a module in V now? This one, you map this W to, let me write it UW. What is UW? UW by definition it is all those elements. This should be a module, a submodule of V. So it is all those elements X in V such that X by 1 belongs to the given W. So this is precisely, we have a W submodule here. This is precisely the inverse image of this W under this iota map. So I V S inverse of W, that is precisely this UW. So if X over S is here, then X over 1 is also here because it is S inverse A submodule, and therefore image is precisely this. So from a S inverse A submodule we got a A submodule of V, and this operation U, moreover it is inclusion preserving. Moreover, if W is contained in W prime, contained in S inverse V, S inverse A submodules, then U W is contained in U W prime contained in V, and these are A submodules. What does that mean? That means this is an ordered homomorphism. This is an ordered set with respect to inclusion. This is also ordered set with respect to the inclusion, and inclusion is preserving. That means this map respect the inclusion. That means this map is in fact a homomorphism of lattices. What do we have to check for this? It preserves order and also it preserves the supremums. But supremum is what? Supremum is the sum, but this preserves the sum also. That is very easy to check because we have checked that, and it preserves the intersection also. So therefore, this is a homomorphism of lattices. Moreover, it is injective. Moreover, it is injective. Why it is injective? That means we need to check that if I go back, if W is and W prime they go to the same element, then they are equal. But that is clear from this definition that we have checked that what did we check? So let me see. Since I am explaining why is it injective. Since, let me write in the next page. Since we have checked that if I take W and then go to UW and then go back. So this is A S inverse A submodule, and this is A module, A submodule, and from here we can recover W because when I go push it to S inverse UW, then this is precisely W. This is very easy to check from the definition of UW. Therefore, so let me check this. So first of all, this inclusion is obvious because what is this? This is by definition, these are all those element x in V such that x by 1 is in W. Now when I take S inverse of this, that means I have to take S inverse of all this, but they are, so if x belongs to UW, then x by S will belong to W because this is same as 1 by S times x over 1. X over 1 is in W and therefore 1 by S is in W because W was S inverse A submodule. So this is therefore this inclusion is clear. Conversely, if take any element in W, if any y by S belong to W, where y is in V and S is in S, then you, because this is a W is a S inverse A submodule, I can multiply by S by 1 times y by S. This is equal to y by 1. This is also in W. If you like, since W is S inverse A module, S inverse A submodule. So this is an element in S by 1 is an element is S inverse A. Therefore, y by 1 is in W. But that means Y is in UW. But Y is in UW, then UW is a then S inverse UW, I can take the numerator Y and denominator S, then this will belong to S inverse of UW. So that means starting with an element in Y over S, we proved that Y over S belongs to this. So that means we have proved this inclusion. So altogether we know equality here. So therefore, if you start with W, go to UW and then you can recover W from this. So that means this map is injective. So the map is injective means what? That map is injective means the following. That means if I take the submodules S inverse A submodules of the module S inverse V, that is a sublattice of the lattice of A submodules of V. So this lattice is embedded in this lattice. So this is a sublattice. That means whatever property we have here, they are inherited here, because this is a sub of that. In particular, so in particular what we proved is the following. Let me write what we proved. In particular, if V is Noetherian, respectively Artinian, then A module, then S inverse V is Noetherian, respectively Artinian, S inverse A module. Remember, when is what was our definition of V is Noetherian? That means the ordered set SAV with inclusion is Noetherian ordered set. That was the definition of Noetherian. The definition of Artinian, that means this ordered set is Artinian. Artinian ordered set. What is the Noetherian ordered set? That means every non-empty subset has maximal elements. Here every non-empty set has minimal elements. And the dual of one way to say is that dual of this is Artinian. Therefore, we remember so many things we have checked at once. By checking Noetherian, we also checked it is Artinian, because changing the order. Not the same module but the opposite theorem, the dual theorem. Alright, so this is obvious, because this ordered set and this ordered set S suffix S inverse A, S inverse V, this inclusion, this ordered set is a sub, this is a sub of S A V, same inclusion, and sub which preserve the orders are same. Therefore, we have noted earlier that Noetherian subset of a Noetherian ordered set is Noetherian, subset of a Artinian ordered set is Artinian. Therefore, these are now trivial statements. In particular, so this is 1, 2, A, the ring A is Noetherian, respectively Artinian, ring, then the ring S inverse A is Noetherian, respectively Artinian. This is because what are the submodules of the ring A as a module? They are precisely the ideals in A. So, and then these ideals in A with this is an ordered set. If A is Noetherian, the definition was this is ordered set is Noetherian, and Artinian means this ordered set is Artinian, and same argument that ideals in S inverse A, this ordered set is a sub of IA natural inclusion. This is a sublattice. Therefore, subset of an ordered set, subset of a Noetherian ordered set is again Noetherian, subset of a Artinian ordered set is again Artinian. Therefore, these are trivial statements. But a little bit more than this I want to write what happens to the generators. So, this is I want to write this as an example. Let us write this as an example. So, let A be a ring and S contained in A be a multiplicatively closed set closed subset, and V be an A module. And suppose Xi I in I be a family of elements in V. And remember our notation that when I write this sum I in I, this may not be finite family, it could be infinite family, it could be countable, it could be uncountable. So, if I write this notation, this is the sum, this is the smallest A submodule of V containing all Xi, and therefore, we have described what are the elements. Elements of this submodule are precisely the finite A linear combinations of the family Xis. Alright. So, obviously given a family of elements, we have a map. So, this can also be described as following. You have this module A power I round bracket I. Remember, this is a free module, this is a free A module with basis EI, standard basis is EI. Well, what is this by definition? This is a subset of the product set A power I. These are tuples AI, I in I, and these are those tuples AI here if AI equal to 0 for almost all I in I. So, you are taking those tuples and that is a submodule, and obviously any element of this tuple, any element of this module is actually a finite sum, because this tuple, this AI tuple AI in A power round bracket I, we can write this AI as summation AI EI, I in I, and this is indeed a finite sum. because only finitely many AIs are non-zero. So, it is really a finite sum. So, we have this free module with this basis, and the map from the free module, if you want to define an A module homomorphism like in a linear algebra in a vector spaces, it is enough to give values on the basis elements, and then it can be uniquely extended to the module by extending to the linear. So, we have this homomorphism EI goes to Xi. This is A module homomorphism. This is therefore, where will any element will go? Any element this tuple AI, which is in A power round bracket I, this will go to summation AI Xi, and this is really a finite sum. This is again finite sum, because only finitely many AIs are non-zero. So, it makes sense, and the image of this, if I call this as F, F is an A module homomorphism, image of F is precisely the sum module, sum module. That is also obvious. So, when is this map surjective? That means this image must be whole V. That means this Xi is a generating system for V. So, let us note that. So, this map F depends on this family X. So, I will just write suffix X. Alright. So, therefore, this A Xi I in I, this submodule is a whole module if and only if the map Fx is surjective. And this means, so this condition means the family Xi I in I is a generating system. For V, that means this. So, this is if and only if, and this is if and only if. So, to check somebody the generating system, we have to check that this map is surjective. But we know now what happens if I apply S inverse to this. See here, this Fx was a map from the module A power round bracket I to V. This is Fx. This is A module homomorphism. So, when I take S inverse, that is S inverse of this to S inverse of V, and this is map is S inverse of Fx. But if this is surjective, then this map is also surjective, that we have checked. And what is this map? This map is defined by take any element here, for example, where is EI by 1 will go? EI by 1 will go to apply Fx to EI and then by 1. So, this is F of Fx of EI divided by 1, but this is Xi by 1, and this is surjective, means it generates. So, that is if and only if. So, what we proved is, because this is surjective, then the conclusion is Xi by 1 in S inverse of V I in I is a generating system for the S inverse A module S inverse V. So, what did we check? If you start with a generating system for V, then that implies Xi by 1 is also generating system. So, the number is same. So, if a module V is generated by one element, then S inverse V is also generated by one element, because the number is not changing. So, what we as an immediate consequence is, if A is a PID, principal ideal domain, then S inverse A is also a PID. PID means every ideal is principal, every ideal is A submodule. So, if that A submodule is generated by one element, then S inverse A submodule S inverse A is also generated by one element. That is what we have proved for general modules. So, alright. Now, we can ask also similar question, what happens when this map surjectivity we have done. So, what is injectivity? Corresponding statement, that is very easy again. The family Xi I in I is linearly independent over A if and only if the map Fx is injective. And also we know if the map Fx is injective, then you know the S inverse Fx is injective. This is what we proved. But then this is if and only if Xi by 1, this family is linearly independent over S inverse A now. If you put together, so together all together if Xi I in I is a basis of V over A, if and only if this map Fx, which is a map from A round bracket I to V, is bijective. But this means the map Fx, S inverse Fx, this is a map from S inverse of A round bracket I to S inverse V, but this is also same as S inverse A and then outside bracket round bracket I, because S inverse commutes with the direct sums. So, this is bijective, but that means this family Xi by 1 I in I is a basis of V. So, that means if you have a free module, then S inverse is also, this is basis of S inverse V. As S inverse A module. So, this means, so what we proved is, if you have free modules goes to free modules under this correspondence. See, we have defined no A, the ring A is here and the ring S inverse A is here. So, if V finitely generated, remember we called it finite, then S inverse V is also finite. This is what we proved. If this is Noetherian, then we have proved this is also Noetherian. This is Artinian, then also we have proved this is Artinian. If this is free, then we have proved this is also free. So, good properties are carried over to the S inverse A. So, this is very useful concept. Moreover, also if V splits as a direct sum here, then S inverse V also splits as a direct sum of the same copies S inverse of Vi. So, these are very useful when you want to prove some properties about rings and modules over a ring, and then you make a suitable localization. So, the property carried over that, and then that in the new ring it might be simpler to prove some assertion. That is the reason why we are comparing all these properties. Alright. So, with this I will stop today's lecture. So, we have now quite a bit properties of localization, and in the next lecture also I will discuss a little bit about radicals, that is Jacobson. We already discussed about nil radical. Now, another radical ideal which is very important in the geometry is radical ideal, that I will do it in the next lecture, and the lecture after that I will go back to geometry and study the topology, more properties of the Zariski topology, and use them to prove the first cornerstone in algebraic geometry called Hilbert's null Standards. Thank you very much.